So it's 11 o'clock. Time to start about the next session about myths, about SQL performance. And what I mean with these myths are things like a lot of developers always believe in some miracles, like, for example, that you don't have to test anything. If you have performance problems, you can just add more resources, add more memory, add more CPUs, create more indexes. If things go wrong, then you still have the possibility to use a few hints or whatever. And in the worst case, you can still ask the DBA to change some inidora parameters. Everything will be good. And in the worst case, when everything goes wrong, then there is still time for a firefighting session. So you ask a performance specialist from Trivatis or any other consulting company that comes, flies in for 1 or 2 days and change some secrets in the database, and everything will be fast. Okay, the reality is slightly different, and that's what I want to tell you in the next 45 minutes. My name is Dani Schnider. I work for Trivatis since more than 20 years, mainly in data warehouse projects, and I do a lot of performance tuning, not only in data warehouses, also in OLTP systems, and some of the experience I try to share with you in this session. I'm also a teacher of some Trivatis courses. One of them I will mention just after this. I'm also a co-author of 2 books about data warehousing, and I'm an ACE director, and quite active on Twitter and on my blog, danischnider.wordpress.com. When I say I'm trainer of Trivatis courses, then one of the trainings I give is the Oracle SQL Optimizer and Performance workshop, a 3-day course about SQL performance tuning and how the optimizer works and things like that. And I mentioned this here because some of the examples I will show in this presentation are based on these trainings or on the workshops, exercises of these trainings. Some other examples I created for this presentation, and I'm always looking for nice examples. So last time it was a beer brewery, or sometimes it's a whiskey database. This time I decided to use something else. Because of the Corona lockdown, we have a lot of free time, especially in the evenings and the weekends. And one of our family projects at the moment is that we look all the James Bond movies again. So all the old stuff from the 60s, still the newest one. The very new one is not yet out, but all the others are available. And that inspired me to use some of the James Bond movie titles and also some characters of James Bond movies in the live demos, and also as the subtitles of this presentation. Okay, let's start with the first Bond movie, Die Another Day, or here it is called Try Another Day. And one of the myths in performance tuning is that performance, that's something we can look at the end of the project. So when development, testing, everything is over. So short before we go live with our database, or even later when the users are already working, then we still have the possibility to change a few settings to make things faster. So we wait until users complain about performance, then we create a few indexes and everything is perfect. That's the myth. But when you look what performance tuning means, you probably read the Oracle documentation. I'm sure that all of you always read in these books and are familiar with it. And one of these books which I really can recommend is the Performance Tuning Guide. Also the SQL Tuning Guide is another one in this area. And at the very beginning of the performance tuning guide, it starts with an overview of typical performance tuning tasks divided in these 3 areas. So we have performance planning, instance tuning, and SQL tuning. One of my first performance reviews I did almost 20 years ago when I started at Trivatis. I had the chance, together with a DBA colleague of Trivatis, to do a review on a customer database, and they had exactly these problems. So they went live with their application and realized, oh, we have performance problems. So let's ask Trivatis, then they come and will make it faster. And that's what we tried to do. So my colleague did the instance tuning. So he looked at all the parameters of the database, system configuration, and so on. And I tried to do some SQL tuning, try to find out which are the slow SQL statements, how can we make them faster. Yeah, we were not very successful, both of us. For example, what I did at this time, that was the typical approach, was to run a tk-prof, so a SQL trace to find out which are the slowest statement. And this statement you see here was the slowest statement that was running within 24 hours, and it was running for more than 3 minutes. Actually, the statement is very fast because it was executed 200,000 times in these 3 minutes. But when you also look at the execution plan, so a table access by row ID, that's the fastest way how you can read a row from table, and therefore actually we don't have any SQL performance issues here. But we have performance issues in the application because all of the statements look like this, or most of the statements look like this. The other type of statements were statements that went through an index with some index hints to read the row IDs from the indexes. There were plenty of indexes, so an average of 20 indexes per table. So the whole application, the whole database was completely over-indexed. And none of the statements I found contained any joins. So there were only selects on single tables. So I asked the customer, what are you doing here? Can you show me your application? And when I saw the application, I was a kind of shocked, because what they did everything in the application that was written in COBOL, as far as I remember. And they used the database only to access the data, so a kind of a file system. And everything else they implemented in the COBOL application. So a join was implemented as a hard-coded nested loop in COBOL, where they read the index, and then with the index they had the row ID, and with the row ID they could read the next row from the table. So the whole application was written like this. This, by the way, was the data model. No foreign keys at all, no primary keys, only lots of indexes on all the tables. The tables, by the way, had all of the tables had abbreviations of 3 letters, so ABC or whatever. So not very meaningful names. So it was very hard to understand what's going on here. And finally, so the best solution for this application would be to throw it away and begin from scratch again and do a complete redesign of the whole thing. Yeah, of course, that was not very polite, and I tried to find a more polite way to tell this to this customer, and for us, so my colleague and me, it was quite hard to write a review document in a diplomatically way to tell the customer that his application, so we cannot help him to make it faster, because all the problems, or most of the problems they had, were not because of instance tuning and SQL tuning, but because of the first step here, the performance planning. And that's very important to know, that performance tuning does not begin when development ends. It begins at the very beginning of every project. So with the system design, with the architecture of the whole system, application design, data model, and all this stuff was wrong here. So also testing, so they never tested with a real amount of data, just with a few rows. And therefore, it's a very bad idea to do an application like this. So that's important to know, that you always have performance in mind and not when it's too late and you already have performance problem, but do it before. Sometimes you still have performance problems and you have to do SQL tuning. And when we go to this yellow part here on the right side, one of the first things everybody thinks of when talking about SQL tuning is indexing. The first part here also mentioned in the performance tuning guide. And indexing, for a lot of people, creating indexes is a synonym of performance tuning. So, we have performance problem, let's create an index. We still have performance problem, let's create another index. The more indexes, the better the performance. Or in other words, indexes are good, full table scans are bad. Yeah, I'm not sure whether this is really so easy. When we look at these two execution plans, so that's the same statement. That's one of the queries of our performance tuning workshop. On the top, you see one possible execution plan for this statement, so the option A, and option B is another execution plan. When I planned to give this session at APEX Connect, I thought we are sitting all in a room and I can ask you who thinks that option A is better, who thinks that option B is better, and then look who says what, but that's a bit difficult here with the online session. But you can do it for yourself, just to check your knowledge about SQL performance tuning. Just write it down or keep it in mind. So I think option A is better because the costs are lower, or I think option B is better because the number of lines in the execution plan is less. So which could be true? No, the second is definitely not the case, and the number of lines has nothing to do with the performance of the statement. The costs have something to do, as we will see later, but it's still not a guarantee that this execution plan is better. What we see here is a typical execution plan with nested loops and index access. That means all the tables are accessed through indexes, typically on primary key or foreign key indexes. And this is a good execution plan if we have only a small subset of data. And the other execution plan, the second one, is also a typical one for a large amount of data. Then we have full table scans, we have hash joins. And when we look at the cardinality here, which is the number of rows estimated by the optimizer, when it optimizes the execution plan, so before it is executed, the number of rows is low here. And when we think that is really true, and in most of the cases it is true, then first execution plan would be the better one, which is really the case here. So the execution plan with indexes is good here. What do you think of this execution plan? Is this a good or a bad execution plan? When we look at it, we have lots of tables that are joined together, all of them with hash joins. All of them are scanned with table access full or table access storage full, because it is executed in a hexadata. And if you are mainly working in OLTP systems, then you probably think, oh, that looks very bad. So we want to avoid full table scans. We want to avoid hash joins. If you're more working in data warehouses, then you think that's a very good plan. And this is the case here. That's a query I was running on an autonomous data warehouse, also for a presentation last year, on my demo database of a brewery. And it's a typical query for a report in a data warehouse. We read a lot of data, so we read almost the whole tables. I think here we are interested in the beer orders of 1 month for all customers, and we want to know all these detailed information to create the report. And at the end, we do a group by, and we'll have only 56 rows. But to calculate or to aggregate these 56 rows, we have to read a lot of data, and for this kind of queries, a full table scan is much better than an index scan. So full table scan or index scan, so here it is a good execution plan. So the question is, an index better or a full table scan? There is not one or the other. The typical answer is the typical consulting answer. It depends, and in this case it depends on the selectivity of the query. The selectivity is the percentage of rows or the percentage of data that is selected from the whole data set. If the selectivity is small, that means only a small percentage of the data is read, then we have a so-called strong selectivity, and then the index scan is the better choice. If we have a weak selectivity, that means a high percentage of data, then full table scan is better. So if we read the whole table, it's obvious that it is faster to read the whole table in one step instead of going through an index for every individual row. So what means small? What means high? So the percentage. Here I have another multiple choice question which you can answer for yourself. What do you think? What is the, more or less, so a rule of thumb at which percentage of data, or when you have less than which percentage, is an index better than a full table scan? Is it A with less than 80%, B with less than 50%, C less than 20%, or D less than 5%? When I ask this question in my trainings, so the training attendees, quite often they say 50%, and then they go down to 20 or something like that. But the reality, and some people know that, is it is much less. So as a rule of thumb, I always say, it's around 5%. It can be 4%, it can be 7%, whatever, but the percentage is quite small. That means if you read, let's say, 10% of the table, it's faster to read 100% and throw away 90% of the rows in the result set instead of going through the index for 10% of the data. Of course, it depends on the size of the table, on the data types and the index size and so on. But I will show you how this works in a first live demo. And the live demo, that's usually something you can only see when you're live in the session, whether on-site like now or really in the room. But if you see only the slides, you will miss this part, so that's for your eyes only here. Okay, let's start this first demo. For the demo, I use just one table here. I have a table employees, which I created for this presentation, with about 6,500 employees and a couple of indexes on several columns here. And I run several queries, and you always will see whether an index is used or a full table scan is used. The first query is I'm looking for an employee with last name Bond. We have an index on last name, so hopefully this index is to be used, which is the case. In this case, an index range scan is performed, which makes sense if we read only one row of 6,500. If we do a last name like B%, so all names starting with B, the result will be 444 rows. One of them is James Bond, but we have plenty of others. This 400 of 6,000, that's more than 5% or more than the optimizer thinks that an index is good. In this case, a full table scan would be performed. And that's really because of the selectivity. So if we run a similar query, but we say last name like Q%, we have only 3 rows returned. The first one is the famous Q, you probably know from the James Bond movies. And for 3 rows, even with a like, it is possible then to do an index range scan. We have another index on an attribute with only 2 distinct values, yes or no. That's the attribute license to kill. And if we want to see which employees have a license to kill, of course, we have only 9 of them, only the 00 agents, James Bond, and all the others, we don't know their names. So it's top secret how they are called. But all of them, so we have only 9 rows of more than 6,000. In this case, the index is used, even if we have only 2 distinct values. That means even for these cases, an index can be useful if we have this kind of data distribution. But of course, all other employees with no license to kill, that's much more. So we have more than 6,000 rows here. The full table scan is performed. Okay, let's look for Moneypenny. You know the secretary of MR6 is called Moneypenny, Miss Moneypenny. And if we look for last name like Money%, only 1 row is returned, and therefore index range scan is used. If we do it the other way around and we want to find all names that end with penny, then we also have 1 row. But in this case, the index cannot be used because the percentage, so the wildcard is at the beginning. And that means for the optimizer, or that means for Oracle, it has to scan the whole index in this case, because it can have a name with A or a name with Z ending with a penny, and therefore index range scan is not possible. And in this case, when you have a percentage at the beginning, index doesn't help. We still have a full table scan that is used there. And by the way, the estimated rows in this case is always 5%. So these 323 rows is exactly 5% of the whole data set. That's always the case with a percent at the beginning. Okay, we are almost at the end of the demo. So now we know that Miss Moneypenny has the employee ID 123. And if we know the primary key, so we can access to the primary key. And here, because the primary key has always an index, a unique index, I would think that the index unique scan is performed. Let's see whether this is the case. Oh no, something went wrong. Why is the full table scan done here? And that's a typical problem that you sometimes see when, as soon as you use functions in your where conditions, then an index cannot be used unless you create a function-based index. And here the function toNumber is used, although it is not part of the query, but the implicit type conversion is done. Why that? In this case, the employee ID is not a number, but the varchar2 column, because we want to store the 00 numbers. So the 007 should be stored as a 007 and not as a 7. And therefore, the developer of this application decided to use a string as a primary key. And if we have a string, we also have to use a string in the query. Otherwise, a type conversion can be done. That is really bad when the index is not used in such a case. So to correct that, we of course have to add or to define the constant as a string here. The same is, by the way, for dates. So never use a date just as a character. Always use the toDate or the to timestamp conversion of the constant to avoid such problems. And last but not least, that's the longest demo, by the way. Here the index unit scan is performed. all the queries we have seen so far, they use where conditions. So typically an index is used in combination with a where condition, with one exception, and that's a count star. So if we want to see the number of rows of the employees table, we can do a select count star. And surprisingly, when we look at the execution plan, we see that an index is used here, and here the index on the attribute license to kill, a so-called index fast full scan is performed. Because the optimizer decides, okay, it is easier to read the whole index, which is smaller than the whole table. So an index fast full scan, it's kind of a full table scan on the index, is faster than to do a full table scan. And why does it use this index license to kill? Because this is the smallest index on the table, the smallest index on a column which is defined as not null, otherwise it would not work. But this is the answer of another myth that is quite often used. So a lot of people think that count star is not really fast, so we can make it faster if we do a count one or a count on the ID of the table or whatever. Actually, it doesn't matter. Even if we do a count one, it uses exactly the same index. So don't care about what to write in the count. So if you want to see the number of rows of the table, then you can use count star or count constant. It doesn't matter. But what matters is the not null constraints on the column. So license to kill is defined as not null. If I change it to null, that means null values are allowed, then it could be that the index fast full scan return less rows. And to avoid that, Oracle does not use this index anymore for the count star. And if I do a count star again, it would use another index. So in this case, the index on the foreign key and the department ID, which is the second smallest index on the table. So there are several options. Indexes are a really good thing, but as you have seen in this demo, not all of them are, not always an index is the best choice. Sometimes a full table scan is faster. Okay, live and let buy, another myth. If performance is bad, we just can add more hardware. So that's what often helps. And that's also one of the basic principles of the autonomous cloud databases of Oracle. So for example, if you create the autonomous data warehouse in the cloud, you have the choice to scale up and scale down the number of CPUs, and that also affects the amount of memory that is available. And that means the more memory or the more CPUs you have, the more resources you have, and the faster your query would run. And that's the recommended way of Oracle to do performance improvements. If your load jobs, for example, run too slow, then you just scale up number of CPUs. Of course, it costs a little bit more, and you have in the background, there are in the data centers, you have Exadata available, perhaps not the whole for you, but you have a plug of the database on this Exadata, and if it's not fast enough, then you can just use more resources on this Exadata. You even have the possibility to add another one if it is not enough, or a third or a fourth or a fifth. So the more hardware you have, the faster your query and your jobs will run. Some people call this the Kiwi approach, kill it with iron, and that means yeah, just add more hardware and it will solve your problem, which is actually true, but it is not the solution for all cases, as I will show you in this demo. No, that's not a demo, but an example I once saw when I did some performance tuning for a customer. What they had is that was a data warehouse that was originally developed about 20 years ago on a DB2 mainframe database, and a few years ago they moved it to an Oracle database on Exadata on-prem in this case. and some of the queries were running faster, some of them were running slower. And one of the query this here was running for about 1 hour, and then it stopped with an error message, unable to extend the 10th segment in the table space, in the temporary table space. You perhaps know this message. And what you could do in such a situation is increase the size of the temp table space. That means instead of having this error message after 1 hour, you will have it after 2 hours, but the problem is not solved. So the problem in this case was the query. Fortunately, the query looked like this, so it contained several with statements. Each of them could be executed separately. And then the main query does a select distinct and joined all these with queries together. So to test it, I just executed one step after another. So the first few went quite fast. And then at one point, I realized, okay, this takes much more time. And then I looked at this query here, and which was still complicated, but not as complicated as the whole statement. And then I realized that one of the join conditions was missing. That means a Cartesian product was done here in this subquery B. This blew up the whole data set. That's why they did a distinct at the end. But that means that a lot of data or a lot of rows were created. And at the end, with the distinct, they were reduced to the real result set, but that needed a lot of resources. Okay, so we have two choices here. We can increase the temp table space, or we can add the missing join condition. If somebody thinks that option A is the better choice, yeah, probably not a good idea. It's obvious here that changing the SQL statement is the much better solution in this case than to add more hardware. Okay, that's another example. I don't show it live, it will go too long, and I cannot reproduce this case anymore because I don't have the details anymore. But what I can show you here is how we can do performance tuning with hints. That's also quite often used. So when we have a poor execution plan, we can add some hints to tell the optimizer what to do, and that's also very nice. But a lot of people have not sorry, put on screen. Do not really know how hints work, and I think it's something magical like this one. So here we have a query that runs more than 3 seconds to read only one row. Even if I repeat it, even the second time, it is still very slow, so still 3 seconds. But what I can do here, I can add a hint, the golden hint, and then if I run the query, it is much faster now. So that's what a lot of people think, that that's what performance specialists do. They come, change a hidden parameter, undocument the parameter, or add just some hints, and then everything is fast. And with this hint, that really helps here. And if I run the same statement again without the hint, then it is slow. That here you see the golden hint solves the problem. Yeah, that works here on my demo database, but it does not work in reality because the concept of hints is slightly different. A hint, with a hint, you can define that the optimizer should use a particular index or a particular join method or a join order or many other things. And what a hint, what we do with a hint is we cut some branches of the decision tree of the optimizer. The optimizer creates several execution plans and decides to use the cheapest one. In this example here, a join of 2 tables, T1 and T2, and the optimizer creates here 9 different plans or even more, and the cheapest one is this with the cost of 47, and it decides to use this plan, which uses, for example, index 1 on the particular table T1. But we want to tell the optimizer to use index 2 instead, so we add a hint. use this index. And that means we just cut this branch. That means we don't allow the optimizer to use this index anymore, but this instead, and hope that the optimizer chooses this plan, which is not the case because the optimizer does the same as it always does. It chooses the cheapest execution plan of the remaining decision tree, and that's the one here on the left. So it chooses a completely different execution plan, so not what we expected. And to tell the optimizer that it has to use this one, we sometimes have to add more hints. In this case, for example, if we add a leading hint and say, okay, you have to start with table T2, so we cut the whole branch here, and then this is the cheapest plan, and in this case, we are lucky that this plan is used. Okay, on PowerPoint, that seems to work, but how about the reality? Here I have an execution plan of a join of two tables, which return only one row, once again. And I expect that the nested loop is performed here because that would be the best plan for such a statement. Okay, the optimizer decided to do a merge join, a different join method, and I know it better because I'm a performance specialist, and therefore I tell the optimizer to use a nested loop. I add a hint, do a nested loop on the departments table, so start with the employees table and then you use a nested loop. And what is the impact? Nothing changed, so we still have the merge join here. And why that? Because the optimizer still starts with a departments table, and then when it goes to employees table, it can choose what join method is the best. And because there is no hint about the join of the employees table, it uses what it used before, the merge join. And the hint use NL on departments table is ignored because there is never a join with the departments table, because this is the table that is read as first, so the so-called leading table. Okay, if departments is the leading table, we probably have to use a nested loop on the employees table. So I add another hint and say, okay, use NL on E, which is the alias for the employees table. And in this case, still not a nested loop, so it's even worse. Now the optimizer decides to do a hash join. Why that? It wanted to start with departments table, but said, okay, in this case, it does not make sense to do a nested loop. That would be too expensive. So I switch the join order and start with the employees table. There is no information about how to join the departments, so I use what I want, and in this case, it decides to use a hash join. If we really want to be sure that the execution plan is executed that we provided, then we have to add all the hints that tells the optimizer to do the right thing. That means we have to tell it, okay, start with the employees table and do a nested loop then on the departments table. And finally, we have the plan that we expected. It's not faster than the previous one because the amount of data is too small, so all of them are fast, but the costs are higher than the original plan had costs of 8. This one has costs of 10, so slightly higher. And that's typical. So whenever you use hints, that means that you tell the optimizer to do something else. So you cut some branches, and that means that some of the plans are not possible, and then from the remaining it uses the cheapest one, which is usually more expensive than the original plan without indexes. Okay, almost at the end. I skip one part because then we have some time on. First, I want to show what was done here in this demo. So what we have seen is this was the original plan. The optimizer used this plan with the merge join. Then we added the hint, which says you are not allowed to use a hash join on a merge join here, but that doesn't matter because it still uses this plan. If we cut this possibilities, it goes to the other direction. And if we have 2 hints, then it had only this choice and use the plan we were looking for at the beginning. Okay, no time to lie, or not no time to die. That will be the next James Bond, which will come out in November this year. And that's the summary of this presentation. So we want to see which of the myths are really true and which are not. Here a couple of questions which can be true or false. So the first myth is performance should be considered after the development. As we have seen in the very first example, that's definitely a bad idea. So performance is always important. More memory helps to improve SQL performance. Actually, that's true. It's not true in all cases, but often this TV approach really helps to improve performance, but it's not always the cheapest approach. So it's much better, if possible, to rewrite the statement or perhaps add another index. But adding more indexes is not guaranteed that it always improves performance. So too many indexes can even slow down the things, especially insert, update, delete, and also confuse the optimizer if there are too many indexes available. Full table scan is slower than an index scan. That's definitely not true. That is true for small result sets, but it's not a general rule. Count 1 is not faster than a count star. It's exactly the same execution plan. Hints can force the optimizer to use a specific plan. Yes, but only if you add enough hints to tell the optimizer what it really has to do. Otherwise, you have some problems, as you have seen in the last demo. What is definitely wrong is that hints reduce the costs of the execution plan. It's the opposite. So as soon as you add hints, then the costs will increase, but the response time can, if you use the right hints, still be faster then. Yeah, how about the golden hint? Makes every query faster. That's obviously not the case. You can try it on your databases. It will not work. But the last myth, that James Bond always wins, that's as we know from 24 James Bond movies so far, that's definitely something that is true. So that's the only myth that is still true. All the others are partly true or even false. Okay, we are finished there at the end. There is one little detail missing. If I don't show it now, then I think that will be one of the first questions. How about the golden hint? So why does it work on my database? And I can show you the secret behind it. So why is this query so slow? 3 seconds, and why is it much faster with the golden hint? What I did here is I created a SQL plan baseline for this statement, changed it. So I told the optimizer whenever this statement is executed, then use, where is my mouse? Then use a predefined execution plan, which is a very bad one. It does a hash join. It starts with the biggest table and does a nested loop with 3 full table scans then, which is definitely not a good plan for this query. And whenever this statement is used, when exactly this statement is used, then this SQL plan baseline would come into place. But as soon as I change the statement, for example, with a comment or with a hint, which is not a real hint, but just a syntax error, for example, the golden hint, then it's not the same statement again, and then the optimizer chooses its own plan, which is of course a much faster plan. And the hint report, which was introduced with Oracle 19, it shows you which hints are not used, and in this case the golden hint is not used because it is not a known hint to the optimizer. Okay, that's the secret And so the myth of the golden hint, this hint doesn't exist. So I hope you never have to use it in your databases. Okay, thanks for attending. If there are any questions, I think Tobias will let me know now. I haven't looked at the chat yet. Are there any questions?
Thanks, Dani. So far, I couldn't see any question. There's just one comment by Volker Deringer. He said polymorphic table functions is something you can, there's always something you can learn about listening to presentations. So it's more a comment. So he learned something new.
I've got polymorphic table functions. That's a really cool feature of 19C, but I think that would be a completely separate session because it's a lot of functionality which is part of it. So I think there is also a session. I'm not sure whether one of the sessions is planned on APEX Connect, but I think there are several sessions on this also available.
Okay, there's one question came. How can I enable the statistics on my database?
How to enable the statistics on your database. So the statistics are always enabled. That means you just have to make sure that they are refreshed, that they are always up to date. And by default, there is a job that runs every night, by default at 10 o'clock, which regathers statistics for tables with more than 10% of changes. So if you don't change anything of the database, then normally your statistics are more or less up to date, and that means you always will have, in most of the cases, stable execution plans. In my demo, I gathered the statistics directly before the demo because I want to be sure that I always have exactly the same behavior, even if I rerun the statistics in a couple of months on a different conference, for example.
Okay, so well, that has been all questions so far. So thanks again for your.
That looks good. That means that most of the attendees don't believe in myths and either already knew it or are now learned some of the myths were not.
Well, maybe it's a good thing in times like this. Okay, so thank you again, and we will go into